Good day, my name is Kate and I will be your guide for today. We are in Optics Museum now, which located in ITMO University. And what is optics? Optics is a branch of physics which studies light and its interactions with matter. And the most interesting and one of the most complex applications of light is in this hall. Here in the white showcases you can see beautiful objects from the Moscow Museum, the Diamond Fund. And all of those exhibits are in Moscow Kremlin now. These are not copies or illusions, they are holograms. And it's the best quality of the hologram which scientists can make nowadays. Such holograms are called optoclones. And if you look at such hologram, you can see shadow and you can see beautiful light effects on gems. But you can make sure if I tell you the truth or not. Look from the side at this hologram and then you will notice that the image becomes blurry. Here you see holographic setup which was created by Russian scientist Yuri Denisyuk in 1960s. According to the scheme, such ultra-realistic holograms are recorded all over the world to this day. If it's necessary to make a hologram of a huge object, then another method of holography is used: digital. Such holograms are based on 3D model. Computer makes an interference pattern of 3D model. This pattern then printed on the surface of the photofilm with a special holographic printer. It is called a holoprinter. Moving relative to digital hologram, you can notice cars driving across the bridge. So you can see it's not just a model, it's a real photos of a real building. Due to digital holography, it's possible to create a 3D image of a non-existent object. You see a hologram which contains 4 floors of one building. Go around the hologram. From each new angle, you will see different floors: underground parking, first floor, second floor, and roof. We can stand still, but also see different floors. If I hover the light source from above, which illuminates this hologram, from different sides, with my flashlight, we will see different pictures. The second history hall begins with a story about an outstanding scientist, Yuri Nikolaevich Denisyuk. He was the creator of method of recording optoclones, full-color holograms. In 1862, he invented the method of creating optoclones, and this discovery happened here, in this building. His photographic portraits are displayed on easels. Next to it, on a showcase, is a photograph of the first holographic setup which he made in his free time. So now let's look at the hologram of Alexander Pushkin bust. Using this huge hologram, I can show you how holograms behave under different light sources and angles. For example, you won't see the picture if I close the light. The picture disappears completely. Then I use my flashlight and you see the picture moving. It changes depending on angle of the illumination. I can move it, rotate, make smaller or realistic. And also there is an interesting fact how image behaves when there are 2 light sources. You see that dependence on the number of light sources is direct, and dependence of the power of light sources is also direct. Bright spotlight on the floor is much brighter and our pictures almost disappeared. What do you think will happen to the image if you break the hologram into several parts? Will an image of an object be visible in each shard? You see a sculpture consisting of many pieces of holograms. In some of these shards, you can even see the whole image. Each piece of the hologram allows you to see much more than a scarf of a photograph. The point is that information about the whole image is stored in each part of the hologram. So now we ended up talking about holography, and I will show you another properties of light, and we will talk about ancient Chinese mirrors. On the showcase, they are round bronze mirrors 5 mm thick. The front side is slightly convex and the back is decorated with an unusual relief. Such mirrors have been made in different countries, including China, since the 4th century AD. There are magical ones among Chinese mirrors. One of such mirrors is on a stand. The mirror has a relief, a dragon pattern. You can see it in the mirror behind. If you take a magic mirror outside on a sunny day and direct the reflection of the sun's rays into the shadow, then in this shadow, a pattern of the back of the mirror appears. That is, the light seems to pass through 5 mm of bronze. On a white sheet attached to the glass, a pattern appears exactly the one depicted on the back. No evidence of how such mirrors were created has survived, but scientists have found an explanation for its magical properties. The mirrors were made of bronze. This metal is quite soft and therefore easily polished. China did not yet have polish equipment, but there were so-called diatomizers. Diatoms are tiny shells that can be used to polish bronze in 2-3 hours. And the magic mirror had to be polished not with an ordinary polishing pad, but with something like a squirrel brush. According to estimates, this could take about 3 months. The relief itself, on the front side, was created because of heat shrinkage, the technology of heat treatment of bronze. Now let's go further and start between the fronts. You see a regular French press for brewing tea. It seems to you that there is only water inside. Then we lift the press and you see there always have been hydrogel balls. Why do hydrogel balls disappear in water? Not only because of transparency. Most of transparent objects we will not lose in water. For example, usual plastic bag we will see in water. Hydrogel and water are almost the same index of refraction, and light passes through water and balls like there is only water inside. That's why we don't see balls in teapot. A common misconception is that if you drop diamonds in water, we will not see them. In fact, refractive index of diamonds is almost twice the refractive index of water. So diamonds are perfectly visible in water, and it's only hydrogel we can find here. One of the greatest assets of our museum is a collection of 144 reference glasses. This is so-called upper catalog. It was created at the Babylon State Optical Institute, and the color and music accompaniment is the collection and was created by students of the University. Each glass is assigned its own serial number, consisting of letters and numbers. The letters indicate that particular glass belongs to a large class, flint or chrome. On the left side of the collection, there are chromes, and you can notice that there is a letter K in its serial number. And the second large class is flint, and flints are on the right part of our collection. The number of digits after the letter indicates whether the radiation-hardened glass is in front of you or ordinary. In the designation of ordinary glasses, there is 1 or 2 digits. Such glasses are used for the civil industry, the creation of lenses for microscopes, telescopes, cameras, and other optical instruments. Radiation-hardened glasses are designated by 3 or 4 digits. Such glasses are used for military or space purposes. When exposed to radiation, radiation-resistant glass will retain its old optical properties and color. In this room, I will tell you about our properties of vision, and we'll start from early animation and first cartoons. First, our vision is persistent. This means that we can perceive no more than 20 frames per second. And if there is something that is faster than 20 frames per second, the image becomes blurry. And here you see the first cartoons. It's called zoetropes. If you divide the smooth picture, you will see motion and a cartoon. The second zoetropes work the same way. You can also look in the holes and will see a small cartoon. And also you can see the proximascope, where is just the mirror prism, and you see emotion in this prism. Here you see a phonotrope. For our camera, it is a smooth, blurry picture, because our camera has about 60 frames per second. But if we take phone camera, where there is 30 frames per second, then you see a dancing dachshunds. This is a stroboscopic effect. In this hole, there are also lenticular images. You might have seen such calendars, postcards and bookmarks. Such images are also mistakenly called holograms, but the process of its manufacturing is definitely different. It is made using at least two images. Images cut into thin stripe and alternating with each other are printed as a mixed picture. A lenticular raster, many small prisms or lenses, is glued on top. This surface is always gripped to the touch. In our museum, there is also a lenticular display where you can see the 3D effect without using special glasses. Our museum is dedicated to light and color. Quite well-known experiment is demonstrated in this room, colored shadows. First, let's look at three lanterns which illuminate the white wall. It is green, red and blue. And there is an additive color palette. And this color palette is used in our displays and everything that illuminates the light. And if we cover the light and come to the white wall, we see that our shades has different colors. And this is subtractive color models, which is used in color printing. For example, you see there are three colors, magenta, cyan and yellow, and these colors are mixing like paintings on paper. For example, cyan and yellow makes green color. Look at the white screen. You can hardly see anything on it, but if you take framed fields or 3D glasses, you will see the multi-colored pattern on the screen. The film within the frame is a polarizer. Only a part of the accelerations of the light wave, oriented in a strictly defined way, passes through such a film. Highly stretched films, like scotch tape or liquid crystals like on TV screens or displays, change the polarization state of the light. Therefore, looking at such products through the polarizer, one can see a difference invisible to the naked eye in the properties of neighboring pixels or pieces of adhesive tape. In this hole there is a thermographic camera. The infrared radiation is a thermal radiation of any heated object. The device which registers this radiation is thermographic camera. And this device turns heated object into color shades. And you see that the most heated objects are white and yellow here, and which are less hot, those objects are green. And the coldest objects here are purple. We can also make heat marks on our clothes. For example, if we take a warm hand, a heat mark on our clothes. And actually, such vision is what reptiles have. And if you look at the, for example, snake, you see snake from in the terrarium, but you are invisible for the snake when it's inside the terrarium. And also we can make a heat mark here too, on such plate of glass. Lip motion is a small USB device which uses infrared sensors, and it provides wireless connection between human and computer. This is just a controller like mouse or keyboard. The laser harp is also contactless. It works with laser strings, and you can interrupt it with your hand. There is a place where laser beam is emitted and where it should come. And if this beam is interrupted, we hear the sound. And this is how laser signaling works. For example, in metro stations. Here, plasma globes. High-frequency alternating current is applied to these globes. Every glass bulb is filled with inert gas, and also you can see a red sphere or pink sphere. This is an electrode. When I touch the globe, potentials inside the globe are redistributed and current flows along the different paths. And this is an electromagnetic field outside the balls, not only inside, and this is easy to prove by touching a luminescent lamp to them. It becomes glow. So when you touch those globes, you should put off your clocks or metal rings, for example. In this hall are also exhibits. For example, on the right wall you can draw with your flashlight. This wall is covered with the 7 layers of the luminophore, and the second wall is also an exhibit. This wall can freeze your shadow. You just need to take a photo with your flashlight turned on, and then you'll see that on the photo there is only your shadow. And it's not necessary to take a photo, you can even use a short video with the flashlight turned on and the shadow on the video. This exhibit is scientifically called miroscope, but more often it is simply called mirage. It consists of two concave mirrors of identical shape. Strawberry is on the bottom of this setup, and we see its reflection, mirage. This room is dedicated to ultraviolet light. Ultraviolet light has most short wavelengths from that of visible light, but it's longer from that of X-rays. And now all of the ultraviolet lamps are turned off, but I just want you to see this room without ultraviolet. Then I change the light and you will see everything changes too. Pictures on the wall and butterflies are made with fluorescence paints. Scorpio, which is in the chamber, glows green because of hyaline in its shell. And also you can check if your bills is fake or not, or maybe your documents. You can see here Chinese yuans and Belarusian rubles. It doesn't glow such as a white sheet of paper. For example, white sheet of paper is really bright here, but bills and documents are only with the fluorescence filaments glowing. In this glowing hallway, you can also see glowing filaments, and there is no any liquid inside. There are only ink paints, which we saw in butterflies or painting, and if we look at these filaments at dark, and you can see that in the white light, the glowing instantly finishes. In this hall we end our excursion linked with the Museum of Optics. Here is an installation which was made by the student from Itmo University, and this is just like a fantasy about how sound looks and how visual perception sounds. And now we will take a look at the beautiful interiors of this building, and we